Good afternoon, everyone. We are from Group 19, MA2011. Today we'll be presenting topics about sharpening moon images using Fourier series. The technique is called Fourier Transform. Our group consists of Dihan, Terence, Sumin, and Steven. Myself will present about this topic. Okay.
The objective of today's presentation is to have astronauts having a better sighting of where to land on the moon using the concept of Fourier series transformation.
That's the introduction. So what is a Fourier series? As we all have learned that Fourier series is the summation of sine and cosine function. All other functions can be expressed approximately in Fourier series. An image itself is nothing more than a two-dimensional signal, so it can be expressed into f as y function, and of course if it can be expressed in function, we can do the transformation of function. And if it is, as you all can see in the left side of the picture, that picture is nothing more than just array in Python. Okay, so Fourier transform. So what is actually Fourier transform? It is actually image processing tool which is used to decompose an image into sine and cosine function. So this application can be used in filtering and image analyzing and image compression. So how does it actually really works? As we all have known that there is a high pass filter which allows only high frequency to pass through, and low pass filter only allows low frequency to pass through. The exact method of how it works will be presented by my friends. So Dihan, please.
There are three types of Fourier transformation for the image processing. Firstly, discrete cosine transform, or DCT, is a finite sequence of data points used to compress from original image to reconstructed image in order to produce file types such as JPEG. Next, the formal definition of DCT can be expressed by this, whereas x0, x1 until xn are the real number, but we are only interested in the complex form, so the discrete Fourier transform, or DFT, is used, which has this expression. Then finally, the fast Fourier transform, or FFT, is an algorithm that computes the DFT easier and faster. So why are we interested in sharpening images using the concept of Fourier transformation? Back to the objective, to have astronauts have better insight on the moon landing, because back then there were no built-in runways or helipad on the moon telling them where to go. Next, the lunar terrain is made up of three distinct features. Firstly, highlands make up 83% of the lunar surface and resemble mountains on the Earth. They consist of smooth contours and can be seen as older and lighter in color. Furthermore, lunar mare, covering 17% of the surface, consists of large basaltic plains formed by asteroid impacts billions of years ago, visible as these dark patches on the moon. Lastly, craters formed by meteor impacts over millennia dot across the surface with differing densities and sizes. Due to the lower gravity and soft crystalline surface, multiple factors need to be considered, such as the approach path, which is choosing an area with relatively few craters without any obstacles in the way. Secondly, making sure they use the propellant efficiency when landing. Thirdly, making sure the lighting would provide good visibility to assist with visual identification. And finally, the slope of uneven ground to allow the lander to have a stable landing. During Apollo missions, landing sites near the equator and proximity to different surface features were preferred, with geologists scrutinizing the pixelated photos from probes to find suitable sites which had been selected months in advance after careful planning and calculations.
Regarding benefits of using Fourier transform, one area of interest is in surface analysis. Typically, images taken by probes in lunar orbit are blurry and low in detail when enlarged for analysis. In the image shown, which was taken by the Japan Aerospace Exploration Agency, when the image has been enlarged to this scale, not many surface features can be seen, and many might be lost due to the low resolution. This is usable for manual processing, but autonomous operations will not be able to discern, and many of these small obstacles might be critical. By applying high-pass filters over the raw data, the image is sharpened and more details and features are more easily discerned. The computer-generated image of the lunar surface will be the ideal output, as the image shows all details and high quality, and on top of it, further processing involving Fourier, such as the analysis of the slopes using mean brightness, can be performed. These techniques will be essential for planning landing sites for future lunar missions, as historically, even the Apollo missions were only able to land at the target site once, and required last-minute adjustments due to features that were not spotted when planning, such as Apollo 11, when the landing site turned out to be a crater which was unsuitable for landing. Branching from surface analysis, autonomous operations on the Moon, such as automated resupply missions or autonomous probes, will make use of machine learning algorithms to make decisions. These algorithms require high-quality data in order to make the proper decisions. One way to obtain the data is by applying edge detection in various forms. Operations will be able to proceed in a wide range of lighting conditions. As the Moon can approach periods where it's pitch black and lighting unfavorable, this would be essential to ensure long-term operations. Lastly, by enabling more data to be used, autonomous operations can operate with greater certainty. This could be applied into automated launches and landings without the need for human guidance and will be the start for auto resupply missions.
Here is an example of how filtering works. By moving parts of the image in the frequency domain, we can achieve different filters of the original image. Now in the next image shows that how the FFT removes the black dot patterns. And so FFT provides the frequency domain utilizing the center of frequency domain. A high pass filter is obtained. The high pass filter highlights the higher frequencies in the image to obtain a sharper image. Now my team has used Photoshop to show an example of how this image gets sharpened here and what is the outcome of the high pass filter that we use. Now passing my time to Steven.
Okay, now I'll be explaining about how we apply Fourier transform to an image using another software. So this software we are using right now is Python. So below is the example of line filtering. So here is the original picture and we will be applying this line filtering to this picture. The purpose here is to make this line to blend in the picture as much as possible. So as you all can see, here is the result of the filtering, and we can see that the line does seem to blend in at the center of the flowers, which the frequency is high, and it is not really blend in at the corner of the picture because the frequency is quite low. So the code was meant to be like that, and yeah, it seems to be work. Next, I will pass my time to Terence to summarize all our topics. Terence, please.
In summary, the fast Fourier transform transforms the image from the spatial domain to the frequency domain. In the frequency domain, we can edit the frequency. This changes the appearance of the image in the spatial area. We can achieve various filter effects by erasing various parts. The fast Fourier transform is used again to convert the image from the frequency domain to the spatial domain. This gives astronauts a higher chance of landing on the moon successfully. Thank you, professors and judges. This is a reference slide.